So let's welcome Raghav Govind from Jefferson Lab. He'll be giving us a talk in the seventh gauge gravity by the Ghats seminars, and he will be talking about SYK model on a noisy quantum computer. So Raghav, yeah.
Okay, so thank you very much for the invitation. I'd like to thank Gaurav, Prasad, and Sachin for inviting me to talk about some work I've been doing in the past year or so with Asad and Bharat. Bharat is a graduate student at Syracuse. Asad is recently started his first postdoc at Iowa. And this is based on this paper, which we put out 2 months ago, and there's some upcoming work. Okay, so let me start with a very brief outline of how the talk will go. So the first thing I want to mention is the entire idea of holographic duality, or say, for example, gauge gravity duality, where certain gauge theories are related to certain in certain limit, gauge theories in certain limit, large and strong coupling and so on, are related to some quantum gravity on some background in some limit. And then these things are broadly called as gauge gravity duality or holographic duality. These are not just restricted to supersymmetric gauge theories like super Yang-Mills, which you see here, where it was like became popular through the ADS-CFT correspondence. But they have also been extended to things which are not gauge theory, for example, condensed matrix system, such as SYK model. And my research over the past 5 years has broadly concentrated on numerical approaches to holography, and it started with lattice Monte Carlo simulations of, say, supersymmetric gauge theory, which are done in classical, which are done in classical, uh, 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 which are done classically in the sense that in the large n limit, and this is classical Monte Carlo simulation of lattice field theory, which we know in Euclidean time. But the problem is, if we want to understand, say, for example, even the real-time dynamics, there's no available tool. For example, if I want to study some BFSS model or matrix model which have holographic description in real time and compute, say, for example, correlators, there's no numerical tool available as per. And this is a hard problem. So people always keep thinking about how we can do a real-time dynamics of, say, some interesting field theory. And that is a very much open problem. What I want to talk about then is introduce some quantum gates and how we can use quantum gates or quantum computation in general to do real-time evaluation of such gauge theories or spin models or whatever quantum many body system we want to understand. And how do we implement those unitary transformations or the time evolution operator using the quantum circuits? Taking as example, we'll go back to the idea of holographic duality and consider the SYK model, which is well known to have a interpretation in terms of near ADS2 gravity in the large n limit. And we will consider that model with a very minimal value of n. So n less than 8, which is not holographic. It is holographic in the large n limit. But obviously, with quantum computers, which we have available at the moment, you cannot do, say, n of 100 or n of 50. And in fact, we are the first group who are like properly studied SYK model on a quantum computer. So this is a very, this is the first attempt at this big problem. And I'll show you some results of how it is doing for n less than 8 on quantum computers, which are available via IBM. Uh, and I'll explain that if we just read the answers given by the quantum computers, it does not agree that well with the exact results or the exact diagonalization results. And we have to resort to something which we call error mitigation. And I'll explain what I mean by that. And then eventually I'll close with some summary and future directions of this work. Okay, so holographic duality, let me make it more precise now. So it relates certain supersymmetric gauge theory, which are maximal. By maximal, I just mean that they have maximum amount of supersymmetry consistent with the helicity. And certain supersymmetric gauge theory are dual to this type 2A and 2B supergravity at large couplings, for example, at large value of 't Hooft coupling lambda, which is this G square N. And you take lambda fixed, but large, and you take n to 0, n to infinity, and that is the large and planar limit. And in that limit, you can describe these supersymmetric gauge theories in terms of gravitational theory. This led to a lot of insights into quantum gravity, because I can map a strongly coupled field theory to a weakly coupled quantum system. For example, a classical supergravity solution. So classical supergravity solution, for example, are related to strongly coupled supersymmetric gauge theories. So there was a lot of progress along these lines in the late 90s and the early 2000s. And the well-known of all of these is the ADS-CFT correspondence. But ADS-CFT correspondence is not the only correspondence which was proposed around that time. It was also extended to other super Yang-Mills theory, for example, in p+1 dimensions. We very well know when p is equal to 3, which is the 4-dimensional field theory, which is the n equal to 4 super Yang-Mills, and that is a conformal field theory. So ADS-CFT is well known, but even if the theory or the maximal supersymmetric theory is in lower dimensions, for example, 0+1, 1+1, 2+1, even then there is some holographic interpretation of those theories. And that was in this work by Marlesana and other authors. And this is what was interesting to us, because this relates the matrix model of BFSS and BMN in 0+1 dimensions, where P is equal to 0, to, for example, some classical gravity solutions, supergravity solutions. But there is a problem with holographic duality. Due to the inherent strong weak nature, solving both sides simultaneously is difficult, except in few interesting cases where it is possible due to integrability. For example, you can compute the scaling dimension in n equal to 4 super Yang-Mills, match it to the results from supergravity, and so on. But in general, at finite temperatures, non-conformal field theories, it's very hard to do a particular calculation on both sides. So this is one of the motivation for all the numerical work we have been doing over the past 5 years with the collaborators all across the world. And that is testing.
So I just wanted to make one comment. So the
Yeah, sure.
integrability statement that you made is valid actually only in the n equal to infinity limit.
That's right. That's right.
So
Also
another thing is, yeah. So second to this question that it's so why are you working with SYK as opposed to, let's say, the BFSS matrix model? Because then SYK, there's a little bit of an ambiguity about whether it is really dual to a holographic theory. Ambiguity in the sense, I mean, it's not as well defined as, let's say, BFSS model, right?
So we have some work already in BMN and BFSS matrix models. What I'm for the purpose of this talk, the emphasis is to use a quantum computer to do something which is useful for holography. And the SYK model is the simplest model we can look into. For example, I would really like to do BFSS on a quantum computer right now, but it's not possible at the moment.
So, but even so, you were working with n equal to 8, right? Here, n equal to 8 or n less than or equal to 8 or something. So, even if n is small in BFSS, it's hard, is it?
Yes, it's just because of the field content of the model is so complicated that it's just hard. But we are looking into it, but it's difficult that we'll be able to make progress like in near future, like for example, 6 months or 1 year. It might be possible after 2-3 years. That's what I'm saying.
What is the immediate reason? So, even if, let's say, you take n equal to 2 BFSS, so what is the immediate?
The immediate problem with doing BFSS is the implementation of the gauge symmetry. How do you make sure that the gauge symmetry is not violating the discretization or the Hamiltonian which you are putting on a quantum computer?
Okay, thank you.
Yeah. Okay. Thank you very much for that comment. Yes, it is indeed at large n. So we see there's another opening for lattice call calculation, and that is finite n, finite lambda. So 1 over lambda, 1 over n corrections can be studied on the lattice. And that is exactly what we did in these 3 papers. We studied finite n, finite lambda, because that's all, you cannot do n equal to infinity on the lattice. So we studied till SU16 for this paper. And we studied up to SU8 for this paper. This is a three-dimensional field theory. This is a 2-dimensional field theory. And the goal of all these studies was to use Monte Carlo simulation to calculate the energy density of the super Yang-Mills theory at finite temperatures and relate it to the black hole energy density. if the gauge gravity duality or the conjectures given in this paper are correct, then both the computations should agree. So on one side, we have a numerical computation. On the other side, we have a computation explicitly using the geometry or the gravity picture. So this is like a non-trivial test of gauge gravity duality on the lattice. And this is the direction which was explored in my thesis, and we wrote 2 papers on this. We wrote several papers, but these are the flagship kind of results we have right now in 1+1 and 2+1. There are other models we are exploring like BFSS and BMN, but we have not published it yet. And these are mentioned in these papers. So basic idea is that everything is still okay if I just want to focus on Euclidean space and look at thermodynamics. But doing real time needs some fundamental change in our way in which we compute. So an important ingredient of numerical lattice formalism is the Wick rotation from the Minkowski space, obviously, to the Euclidean space. Otherwise, we cannot use the usual tricks which we use in Monte Carlo methods, like lattice QCD and things like that. So if we want to stick to real time, tensor networks are one of the promising things which can help us. And this is a direction I've also explored. And we are currently looking at some models in, say, 1+1 dimension, where we are looking at scattering phase shifts and things like S matrix using tensor networks. But the problem is these methods do not scale. So if I want to go to, say, 2+1 or 3+1 dimension, there's no well-known tensor network methods cannot help me in higher dimension. So this is also a problem, that even though we can come up with very smart, innovative classical algorithms, it just seems that at some point you hit this barrier that you cannot really understand the real-time dynamics of a quantum mini body system just on a classical computer. And this is
Sorry.
I'll continue. Hello, is there a question?
Hi, Gaurav, can you mute all the audience members?
Yeah, I am muted it.
Okay, thanks.
No, but I think Vishal has. Yeah, everybody's muted. Yeah.
Okay. If there's no question, I'll continue. So they do not scale. That is one of the problems. So this idea of exploring the paradigm beyond the classical computing was already being explored by several people, by, say, for example, Manin. But Feynman made it popular, and you'll always hear that Feynman 1982 paper or 1970, late 70. But once Feynman wrote this paper, this became extremely popular. And he suggested that we should think about simulating these systems using ideas of quantum mechanics. So for example, we should try to build a quantum mechanical computer. And that is the whole idea of quantum computing. And the basic idea is very simple. Suppose we have been given a Hamiltonian, local Hamiltonian. How do we implement the exponential operator, unitary time evolution, in terms of circuits which exploits the feature of quantum mechanics like unitarity and so on, and simulate that quantum many body system in real time more efficiently than any classical computer? So that is the basic idea. Now, if we look at this plot, we draw circuit depth versus number of qubits which we need. So number of qubits means how many two-state systems which we need. So a qubit is like a two-state system, spin up, spin down. So that is one qubit. How many qubits do we really need to simulate? So if the number of qubits is less and the circuit depth is less, tensor networks can simulate, or even exact diangulation can simulate. But as you increase the number of qubits, or you increase the number of circuit depth, you cannot do tensor networks anymore, and you reach this region which has to be done using a quantum computer. For all the results I am showing in this talk, I would say we lie somewhere around here. So it's very possible using exact methods, and I'm going to show you. And the number of qubits which we use is 4. So it's basically here, the circuit depth is around 300 qubit gates, which is around here. So we are along this line right now. But once we go to more depth and larger number of qubits, we'll be able to do problems which we cannot do efficiently on a classical computer. And that is the whole program of this.
Prasad here.
Yes.
Hi, Raghav. How was this curve determined? I mean, is it just a present day limitation or it's a fundamental limitation?
So this curve was basically, it's not to scale in some sense, but the idea is that different people. So for example, suppose if you take a Ising model, for example, you say, okay, it's on some number of qubits and I can simulate or compute some quantities like magnetization exactly. And if you can do the same thing with a tensor network, then you are below this curve. If the Hamiltonian is, say, for example, local Hamiltonian, for example, which has certain nice properties that the ground state entanglement scales at some limit. So the entanglement is less, then you are in this. But if you increase the entanglement of if the ground state is highly entangled, then there is no well-known tensor network methods we can simulate it. So that is how this is just drawn, but this is not to scale.
That's okay. And if tensor networks can't simulate, basically any classical algorithm probably cannot simulate. Is that right?
That's right. That's what I mean by tensor networks can't simulate, because the best classical algorithms most of them are tensor network based. So if when I say that tensor networks can't simulate, I mean the best scaling algorithm cannot simulate. Yes.
Yeah, got it. Thank you. Thanks.
Yeah, thank you for the question. Yeah. Okay, so now we want to think about universal quantum computing. What is the universal quantum computing? It's very simple to the idea of the digital electronics, which we all studied in, say, undergrad, for example. If you have, say, NAND gate, NOR gates, there are some certain gates with which you can do any classical computation. So, for example, if you have transistors built up of AND gate or NAND gate, there are certain logic gates which are universal, for example. So also in quantum computing, we have to think about what are the universal set gates. There are two approaches primarily. There might be others, I don't know, but two are more interesting. One is the qubit-based approach, and that is what this talk is going to be. So qubit-based approach is saying that the quantum computing can be achieved, or the universal quantum computing can be achieved if we just utilize and manipulate a two-state quantum system. There are more than 24 approaches to make that two-state quantum system. Two most popular are the superconducting qubits and the trapped ions. So superconducting qubits is based on the idea of Jefferson junction, where you have two superconducting layer and you sandwich something which is non-conducting in between, and that can mimic a two-state system. Or it's based on trapped ions. For example, you take some periodic table, the group belonging to some periodic table, take out an electron, you're just left with some charge, and then you apply some voltages and manipulate to create a two-state system. So both of these create a two-state system, different ways of creating a two-state system. And this is a qubit-based approach. But qubits are not the only quantum mechanical system we study. We study the most famous thing we study in quantum mechanics course is the harmonic oscillator. So that approach is called as a Q-modes approach. It is less known for the general audience, but the idea of Q-modes is to use a single harmonic oscillator which has an infinite dimensional Hilbert space. And the best example of that is a photon, for example. And use those photons and make the photons interact such that you can manipulate and achieve the universal quantum computing. This talk is only going to be focusing on the qubit approach. So I will tell you everything about the qubit approach, but this is also a very popular approach. And this is what we are also looking at Jefferson lab. And this is one of the papers which we wrote. For example, we studied the nonlinear sigma model, which is a very famous asymptotically free model in 1+1 dimension, which has a lot of properties similar to the real 4-dimensional QCD, which we all want to solve. But this is like a toy model, and we studied the continuous variable approach to this. So by continuous variable and Q modes, I basically mean the same thing. It's also called continuous variable because everything is written in terms of x and p quadratures. So it's like a continuous, it's not like a two-state system. Okay. Just for someone might be interested, or
sorry, very naive question. So
Yes.
this it seems like the Q modes will be an infinite dimensional Hilbert space, right? So I mean, why is it that it is like, I mean, the reason why I thought like there is a, when you try to do quantum computing, my understanding as an outsider was that number of qubits is sort of the limitation in, error management and all that. So what is it that allows you to work with an infinite dimensional Hilbert space directly?
So when so Q mode's approach is using these photons, but the problem is there are only certain number of photons which you can entangle. Or for example, if you take the Fox state, you can only go up to say Fox state of 15 or 16, 20.
I see.
So you always have certain numbers. So if we cannot deal with like thousands of photons. So the maximum we have reached till now is using sampling method, which is called Gaussian boson sampling, which has tried to deal with like 40 photons. So there is a truncation even in that.
Okay.
But it's like in theory, in formalism, it starts with the infinite dimension, but obviously the limitations cannot take you all the way. There's some truncation on that also.
All right, thank you.
Yeah. So the basic idea of CV, or the continuous variable approach, which is what I meant here, CV, is the Q mode for qubit. It's a qubit-based method is qubits. In this, we have quadrature operators, or the creation and annihilation operators. For these, we have poly operators, X, Y, Z. In these cases, the common states with which you represent the initial state of a, say, quantum system is in terms of coherent states, squeeze states, and number states, which are well known from the study of harmonic oscillator. In these cases, it's 0, 1, spin up, spin down, or plus minus, or plus minus I. In this case, the unitary gates are rotation, displacement, squeezing, beam splitter, and cubic phase. I don't have time to go into the definition, but these are the unitary gates. And in this case, we use phase shift, Hadamard, C naught T. I'll talk about these because this is what we are focusing on. So I'll explain what these are, but unfortunately, I don't have time to explain. But these gates are all unitary and written in terms of A and A dagger. That's the important thing. Okay. So before we go further in the talk, I have to explain what the gates mean, because you'll be seeing a lot of diagrams like this. So just a quick recap of that. If you see a 2 by 2 matrix, it's a 1 qubit gate. If we see a 4 by 4 matrix, it's a 2 qubit gates. And if you see a 8 by 8 matrix, it's a 3 qubit gates. 3 qubit gates will have 3 wires. 2 qubit gates will have 2 wires. 1 qubit gate will just have 1 wire. So for example, poly X is represented like this, which is the poly matrix, poly Y, poly Z. There's a gate called Hadamard gate, which is this. The function of Hadamard gate is given here. If I just take a spin up, pass it through Hadamard gate, it gives me plus, which is equal to proportion of 0 and 1. So I start with 0, I act with Hadamard, I create a uniform superposition. And similarly, other gates have this operation. This rotates around the z-axis of the Bloch sphere. So all these qubits can be represented as a Bloch sphere, because that's a nice way of looking at it, because of the correspondence between SU2 and O3. So this Bloch sphere, or the Riemann sphere, as people also know this as, is that the North Pole is 0, spin up, South Pole is 1, spin down, and then you have other states like plus, minus, and alpha. And these are how you can create, and these phi and theta are the rotation angles. So if you can apply a 1 qubit gate, it will rotate by some angle and things like that. These are all unitary gates. And this is also all unitary gates. And the eventually what we'll have is, we'll want to write down the time evolution operator in terms of these gates. So take any given Hamiltonian of any quantum many body system. The eventual goal is to write down the e to the minus I ht using some approximation, which we will talk about, in terms of these gates. Okay. Okay, so I'll stop here. And if there are any questions, I would like to take them. Otherwise, I'll keep moving to the technical part of the talk. Okay. Okay, so SYK model. So what is a SYK model? A SYK model is a model of n fermions and Majorana fermions, where q of them are interacting at a time. And the q can be some integer from 2 to whatever number you want to have. So it's a model of n Majorana fermions with q interaction terms, q fermions interacting at a time, with a random coupling, which is taken from a Gaussian distribution. For example, the coupling here, which we have, is taken from a Gaussian distribution, which has a mean 0 and has a variance equal to this. So now we can consider any general value of q, but we'll see later that we'll just restrict to q of 4, because that is the most popular version of the model which people study. So we just take q equal to 4. These fermions, Majorana fermions, satisfy this relation. Anticommutator of chi I, chi j is delta ij. And we'll set j equal to 1. This j here will be set to 1. This can be taken something else also, but for our calculation, we just set it to 1. Take set q equal to 4 in what follows. Note that j has dimensions of energy or inverse time. So we'll construct some dimensionless parameters like beta j or jt, which will be dimensionless. This model, in the limit of large number of fermions and at low temperatures, which is beta j much greater than 1, this model has several interesting features and is related to black holes in some special kind of a two-dimensional gravity, which is known as JT gravity. And this model in the large limit develops approximate conformal symmetry, which is related to this the dual picture in terms of the near areas to geometry. So this SYK model is interesting, and this is probably one model where one can compute both sides of the duality at the same time. For example, large N SYK can be solved in the sense that you can have a saddle point contribution in the path integral, and you can also solve the gravity picture. So this is why people are interested in this, because it might be the first model where it's analytically possible to handle both sides of the duality at the same time. One of the things which we want to do with this SYK model is for the quantum computing. The first step is to take these fermions here, chi, and do a Jordan-Wigner mapping. So what we want to do is we want to take the chi's, there are n of them, and map it to these Pauli operators. So for example, Z, X are the usual Pauli operators, Pauli Z matrix, Pauli X, and the I is the identity matrix. So this mapping takes you from the chi fermions to qubits. And it turns out that every Majorana fermion is related to one complex spinless fermion, which can be represented by 1 qubit. So n Majorana fermion will need n over 2 qubits. So if I take n equal to 8 in my talk or n equal to 6, what I'm saying is that I have a quantum circuit of 3 qubits or 4 qubits. So once we do this, we have everything, or the Hamiltonian is completely written in terms of Pauli operators, or the product of Pauli operators, and sum of them. And then you have to sum over different combination of the coupling. You have to combine different quartic terms interacting at a time. Now, the number of terms in the Hamiltonian is NCQ, which just goes like n to the power q. So you have n fermions, and you have to choose you have to choose q fermions at a time, because q of them are going to interact, right? So number of terms in the Hamiltonian is n to the power q. For this talk, we'll just set q equal to 4. And it is clear that the simplest case is obviously when n is equal to q, because you just have one term in the Hamiltonian. So there are q fermions talking at a time, and you only have n, which is equal to q. So there's just one term. And that is what we are going to explain, just to have a good idea about what is happening. Okay, so set q equal to 4, n is equal to q, n is equal to 4. Consider the simplest case. What do we have? H is just this. The Hamiltonian is very simple. This given by J 1, 2, 3, 4 is some random coupling. Chi 1, chi 2, chi 3, chi 4. Now, if I apply this Jordan-Wigner mapping, it's easy to show that chi 1 is this, chi 2 is this, chi 3 is this, chi 4 is this. If I write down the Hamiltonian is just this. It's a 2-qubit Hamiltonian because there's Z and Z. There's a Kronecker product between them, which I have suppressed. So the Hamiltonian is just equal to this minus J1, 2, 3, 4. Z, Kronecker product C. Okay, now if someone gives me this n equal to 4 SYK Hamiltonian and asks me how do we compute the correlators? The first thing we have to do is to write down the exponential operator e to the minus ist to explain the unitary evolution of this. And it's simply given by this. Now, the circuit for the time evolution for this case is very simple. It's just given here. Now, this gate is familiar from the gate which we presented. Is just this gate. So this is control not. It's a 2-qubit gate. And this is just the rotation along the Z direction, on the Bloch sphere by some angle, which is given by the coupling. So it's very straightforward. This Hamiltonian, which is given here, the e to the minus ist, the unitary circuit implementing this Hamiltonian is just this. And 2 C0 and 1 rotation gate is very, very simple to do. It's so simple that we did not do this in the paper. We just showed this is just for example. Now, one of the things which is interesting to know is if I'm given this Hamiltonian, what is the complexity of simulating this Hamiltonian as a function of the number of fermions? So for example, if someone asks me that, okay, you are saying that for n equal to 1, n equal to 4, we need 2 qubit gate, two qubit gates, 1 cube and 1 here. So we need 2 C0 gates, which are 2 qubit gates. So how many 2 qubit gates do we need to simulate the SYK model for a given n? And that is a very interesting problem. But before going there, we have to understand what do we mean by simulate SYK model. So simulate SYK model is, we just want to write down this operator. But for all practical purposes, if H is, say, a big matrix, doing this is not easy. We have to resort to some sort of an approximation or some sort of a scheme, basically. The most popular one which people use is called the Trotter method or the product formula or the Lee-Suzuki-Trotter product formula, where if you have a Hamiltonian written as a sum of HJs, where J is going from 1 to M, where M is nothing but NCQ, then the time evolution operator can be written like this. And this is something which is just coming from this formula. It's a corollary of Hessian-Haas formula. And Hessian-Haas formula is just, maybe you don't know it by this name, but it's like a dual of BCH formula. So BCH formula tells you what is e to the A, e to the B, where A and B are operators. And this formula, which is dual, tells you what is e to the A plus B. So we use this and you can write it like this, and this is what we have. Now, the good thing about this formula is it's just telling us that if the Hamiltonian is sum of terms, I can exponentiate each of the term one by one and multiply it and suffer some sort of an error, which increases like this. Now, once we have a handle and we take control of this, then this is nice because if I have a Hamiltonian as sum of terms, we can exponentiate each of the terms one by one and write a circuit for that. And then that will give me an approximation of this. And that is what most of the quantum computing numerical results you see do. They do this approximation. Now, this is a first order approximation. There are higher order versions of that. We can also apply that. But for our purposes, this is good enough. Okay. So there are a lot of old works. People have explored this problem right after the SYK model was proposed in 2015. There was this paper by Garcia Alvarez in 2017. There's a paper by Susskind and Swingle in 2020. There's another paper by Babush and al. In 2019. They use different methods. The first two are using the Trotter method, which is this. The third method is something else, which is not this method, but some other method. But the problem with third method is that it's not implementable in the quantum computers which we have right now. It's in the fault-tolerant quantum computing, which is like still several years away. So for our purposes, we want to use this method. And for that, this is the complexity. So if n is increasing by twofold, this algorithm is for a fixed value of t and epsilon. Epsilon is just the error. So when we apply these gates, there are some sort of error which we incur, and that is denoted by epsilon. So the complexity goes like n to the 10th t squared by e. So if I fix t squared, t and e, it increases like n to the 10th. And this increases like n to the 8th. These are all very expensive. So what we started with doing was we used some fancy methods, not fancy, which well-known methods, but not so well-known for physicists probably, well-known methods from computer science, and we reduced this complexity to n to the 5. So instead of n to the 10, n to the 8, we now have we just need n to the 5 t squared by epsilon number of gates to simulate any n fermion SYK model up to a time of t where the gates used have an error of epsilon. There's also a possibility of improving this, and this is a work in progress, so I won't say much about that. How do we reduce the terms? So reducing the terms is easy if we just remember one very important thing about quantum mechanics. The important thing is if two operators commute, you can measure them simultaneously. So, for example, when we break the Hamiltonian into, say, m terms, which is scaling like n4, we have to be a little careful in splitting the Hamiltonian. We want to split the Hamiltonian such that we cluster all the terms which are commuting with each other. So for example, this is based on the idea of qubit-wise commutativity or general commutativity. For example, if you have a polystring or the term in the Hamiltonian like x, y, z, z, x, y, right? This is a 6-qubit Hamiltonian, and y, x, I, z, x, y, or whatever. So there's one, sorry, there's a type, well, it should be one less, but yeah, 6-qubit string. So the thing is that if they commute, I put them together. And there's an easy way to check whether they commute. You just see how many places they don't commute. So x doesn't commute with y doesn't commute with x, and everything else commutes. So z commutes with I, z commutes with I, x commutes with x, and so on. So that is a way of finding out whether two strings commute. And if two strings commute, then we club them together and diagonalize it together. We don't use the fact that it can be simultaneously diagonalized. And using these methods, we found out that for different values of n, we need these number of 2-qubit gates. So for n equal to 4, we need 2. For 6, we need 30. For 8, 110. And if we want to go to n of 20 fermions, we need 20,000 qubit gates. Right now, the state of the art is around 300. So we are somewhere between n equal to 8 and n equal to 10. But this is always going to increase. So maybe in the future, we'll be able to do n equal to 16, n equal to 20, and so on. So one of the things we compute is, the observable we compute is the return probability. It's a very simple observable. You start with some state, you act with the unitary time evolution, and then you measure the state again, and you take an overlap, and that is P naught. So if you are at time t equal to 0, it will just give you 1. But if you are at some later time, it will give you some finite number which is less than 1. So we do that, and the results for that is we show that here, for example. So for example, we have 291 C0 gates, 300 C0 gates, and the black lines you see is the exact results in all the plots. So these are 5 different realization of the SYK model, 1, 2, 3, 4, 5. And the 6th one, which is in a different color. I don't know whether it is visible properly, but it's the disordered average over the first 5. So for example, we see that the red is the data points which are coming from the IBM machine. So for example, the black is the exact, the red is coming from IBM machine, which is a little lower than the expected one. But the green one is the data taken from IBM machine, and we add some error mitigation to it. What do we mean by error mitigation? We use some ideas from quantum mechanics to correct the expectation value, which I'll describe. And those are the green points. And it is very clear that most of the green points are in perfect agreement with the black. So what this plot is telling us is that if we read the data from the quantum computer right now, we won't get agreement. But if we are smart enough and we use a little bit of nice error mitigation techniques, we get exact agreement, almost exact agreement with the exact results, right? So that is one of the main results which we have, is that with error mitigation, you can reproduce the results for SYK model to very good accuracy. So there are a lot of things I can say about error mitigation. I don't have a lot of time, but quickly I'll just sketch what it basically means. I've already explained what red and green points are. So the basic idea about error mitigation is that if you have a circuit, how do you characterize the noise? So is there a way of using some principles from physics or say the ideas of quantum channel or depolarizing channel or errors that we can use to improve the uh, signal? And that idea is known as, the major idea is known as C0 only mitigation. It is related to what we use, which is called self-mitigation. The details can be found in this paper, but the basic idea is very simple. If I have an initial state, let's see if I can quickly write. No, probably. Yes. So for example, if I have an initial state 0, 0, it's a 2-qubit initial state, and I apply any number of C0. I apply 100 C0, I apply 1000 C0, I apply 10,000 C0. The output should be 0 and 0. So suppose I have 400 C0s. I start with a state which is 0, 0, and I measure the state at the end, which should be 0, 0, but it is not 0, 0. So what I do is I measure the probability with which it fails to be 0, 0. And that probability with which it fails to be 0, 0 is the error probability, is the error which has occurred just because the gates are not unitary. If the gates were exactly unitary, the error probability will be 0. Or if the decoherence of the qubits was not a problem, the probability will be 0. So once we have that probability, then we can use all these C0 only and C0 self-mitigation. And then we can use the idea of quantum depolarizing channel, which is very well known in quantum information literature. So for example, if you have some density matrix rho, which is passing through a channel which becomes E rho, then the E rho is given by this. Now, if you take P equal to 0 in this, you just get E rho is equal to rho. That means the channel is completely proper, completely unitary. There's no error happening. But in general, P is not 0. And this is what is going to happen to this density matrix as it passes. So we can use this equation because we already know what is the probability of error from the C0 experiment we did. And then we can correct the expectation value using this equation here. So it's simple. You have rho and you want to compute an expectation value. So it's just trace of rho O. So you just multiply it like this. So the noisy value is related to the corrected value by this equation. If P is equal to 1, P is equal to 0, then the noisy value is the corrected value, but otherwise it's not. So we use this equation, and that helps us go from the red points to the green points. So this is what the error mitigation is doing. We are using the C0 only mitigation in addition to the quantum depolarizing channel, and then correcting the value which we are getting from the IBM quantum computers. Okay, in the last 10-12 minutes I just want to emphasize one of the other things we computed for this case, and that is what we call out-of-time ordered correlators. So one of the nice things about SYK model is that there are certain 4-point correlators which are given here, for example, for some operators W and V, which if you compute and look at some time scales, it grows exponentially. For example, if I look at this at after certain 2-point correlators have decayed, the growth of this OTOC is exponential lambda t. And this lambda is known as the Lyapunov exponent. And for SYK model, this Lyapunov exponent at low temperatures, it's important to have low temperatures, is saturated in the sense that lambda is 2 pi t. And this is the reason the SYK model has a holographic interpretation, because to have any sort of, if you take a quantum any-body system and you want to have it some relation to gravity, it has been becoming apparent that it should have this property, that it should saturate the Lyapunov exponent, because it has to have the property that it scrambles information very fast. Because black holes, as we know in the dual picture, are the fastest scramblers. So the quantum many-body system, which saturates the bound, is a good candidate to have a holographic interpretation. These things have been computed very nicely for SYK model up to n equal to 60, which is nowhere close to what we are going to do in the near term with the quantum computers. For example, n equal to 60 has Hamiltonian has million terms, and the matrix is billion by billion. It's hard, but you can still do it. So if you want to have any sort of advantage of a quantum computer for this model, we have to go beyond n equal to 60. And to go beyond n equal to 60, seems it's not very possible, because for n equal to 60, it seems like our estimate is saying that we need an order of billion C0 gates. And we are at like maybe 1,000 right now, even less than 1,000. So there's a huge time to quantum supremacy, at least for this SYK model. So we computed this OTOC also, the out of time ordered correlator for the SYK model. And for that, you have to use some sort of a protocol of measuring OTOC, because OTOC seems very simple enough to write. But the thing about OTOC is that it has an unusual time ordering. So WTVO, WTVO. So it's not very easy for a quantum computer, but there are some proposals, for example, this paper by Swingle and this paper where they propose some protocol to measure OTOC. We use this protocol called randomized protocol, which approximates OTOC, which is given by this quantity, trace of W2, WTV dagger, WTV, as a correlation between two different measurements, one measurement of WT, and one measurement of V dagger, WTV. So I will leave the details. The details can be found in this paper if you're interested. But the main thing is that if we just write two quantum circuits, and the first one measures WT and the second one measures V dagger, WTV, we can compute the OTOC. And that is exactly what we do in our calculations. We create an initial state, which is Q. So this is 3 qubits. So this is for n equal to 6. So we create an initial state, which is just 0, 0, 0. For example, we took 0, 0, 0. And then we act with a unitary. And we have some state. And then we time evolve using the Trotter formula, which we discussed. And then we measure some operator W. And that is what this gives. If you want to measure V dagger WTV, we just insert a operator before applying the unitary just after the state creation. And once we measure this, this will give us the expectation value of this. So now we have one measurement from here, one measurement from here, and you compute the correlation between these two, and that is an approximation of the OTOC, right? So that is what we did. And we ran the calculations on these IBM machines, and we found so we did 3 instances for this model. The first instance, second instance, third instance, and this is the ensemble average over the 3 instances. And we see that, for example, in this case, the blue points are the one which is the simulated protocol. The black is the exact one, and the red is from the coming from the quantum computer. And for small time, there's some discrepancy at the late times, but at small times, more or less, these agree very well. And in fact, the disorder average agrees very well up to very late times. For example, t equal to 9 is what we stopped at. And for that, we needed around 257 2-qubit gates, which is almost the boundary of what we can do with the resources available.
Raghav, sorry.
Yes.
Just a question. What changes as you go from this plot A to plot D?
Nothing changes. So this is just 1, 2, 3 is the 3 instances of the SYK model. So for example, the couplings drawn are different basically. So in this case, I draw couplings, and then I do another experiment where I draw couplings, and then I draw again. So these are 3 instances of the model. And this is an average over the first 3. So what changes is the coupling changes. It's taken from a Gaussian distribution, but the number of samples drawn is different because the number of terms is different. So you have to draw from Gaussian every time. So this is one set, second set, third set. This is average over the first 3 sets. Is that clear?
Okay. Same temperature though, same temperature.
Same temperature,
Three
yes.
different ensembles.
Yes. I'm coming to the temperature part. I have not been very explicit about it. I'll come to the temperature part. But yes, they're all at the same temperature.
Okay.
So
Thanks.
Q is again 4, right?
Yes, Q is again 4. So for example, in this case, the number of terms is 6C4, which is 30. So there are 30 terms in the Hamiltonian. Okay. Now, one thing which I swept under the rug is that there was a row here, right? But I set row to an identity matrix because I set beta to infinity, beta to 0. So now it's sort of a cheating because I said that I look at beta j much greater than 1 for the SYK holographic regime. I'm doing beta now. Doing finite values of beta is extremely challenging for quantum computers. That is what we are exploring right now. So the good thing is if I set beta equal to 0, remember that if beta is equal to 0, then the thermal Gibbs state is a maximally mixed state, which just means that its density matrix is proportional to identity up to some prefactor. And that is exactly why we had this. If the beta was not 0, then you'd see factors of rho all over the place, and it becomes a little harder. So we just set beta equal to 0. This is what everyone does in the literature when they study or talk on a quantum computer for different models. But this is not the region we want to be. We want to be at large values of beta, not at beta equal to 0. So right now we have to come up with some different algorithms and methods and protocols to understand this or talk the same calculation for different values of beta, especially beta greater than 1. And it turns out you need beta of 70 to extract Lyapunov exponents even close to chaos bond, as is known from classical computation. So we can see,
sorry to interrupt.
yes.
So in the so is this the reason why in your OTOC plot it looked like there was some dip at late times? Is that because beta is 0? Because typically I think it saturates, right?
A dip at late time, it might be related. You're talking about these dips up here?
Yeah, so like in these black curves, yeah, exactly. So for instance, on the third plot, it looks like it really is dipping. So usually in these OTOC plots, they are supposed to kind of saturate at some point. If
That's right. It might be effect of the infinite temperature. Yes.
Okay, I see.
Yeah, another thing to note is that all these ideas and arguments about, for example, let me go back to this slide, about this dissipation time, about this scrambling time, does not really make sense for beta of 0 because it is a well-defined thing only for a finite value of beta, not beta equal to 0. But for our purposes, we did beta of 0 because that was the first place you start. But so now we see the problem. We have to go to large values of beta, and we also have to go to large values of fermions, which needs about 1 billion 2-qubit gates. But we are looking into this direction and trying to compute these Gibbs state for SYK model using VQE algorithms. So I can just quickly, I don't have a lot of time, but I can quickly go through this. So the way you prepare ground state, zero temperature ground state on quantum computers is this algorithm, VQE algorithm. So it's a very popular algorithm, and it basically consists of 3 steps. The first step is that you prepare some ansatz on a quantum computer. You prepare a state psi, which depends on some angles, which is given by theta here. Second is that you measure the expectation value of the energy and then try to optimize theta so that the cost function is the Hamiltonian or the ground state energy, and you try to minimize that. And once you have minimized it up to some desired convergence, you note down what theta is, that is the optimal parameters, and you construct an approximation to the ground state, right? So it's an approximation to the ground state. I'm not saying you can exactly prepare, because preparing the exact ground state is known to be hard even for a quantum computer. It's a QMA hard problem. It has a complexity class which is completely different. So this is an approximation in which people compute, for example, if you ask a quantum chemist, people doing quantum chemistry or molecular energies, they use this VQ algorithm on a quantum computer to compute these ground state. But we are trying to extend this using this paper by Celisco to finite energies. So for finite energy, because that is what we need for SYK model, right? We need finite temperatures, finite value of beta. And for finite values of beta, you have a more complicated cost function because now you don't want to minimize the energy, but rather the free energy, which is a more complicated quantity because now the entropy enters and the computation of entropy is not straightforward. So we are looking to this direction, trying to compute the free energy and trying to get an approximation of the Gibbs thermal state so that we can compute OTOC in the future. So these are some upcoming work with some people here, and these are the plots which we have, and we measure the fidelity. So for example, we can measure the exact, we can prepare the exact Gibbs state for these small values of n, and then we prepare one on the quantum computer or the simulator, and then we measure what is the overlap by computing the relative entropy and things like that, or fidelity, for example. These are the plots which we get, and these are for different values of n equal to 8, 10, 12. This is the free energy. This is what we call as the internal energy or the E, and this is the entropy. And this is from a simulator which is called penny lane simulator. So once we have this worked out, we prepare a Gibbs thermal state that we can look at finite temperature OTOC. And that is one of the things we want to do in the coming years. Understand everything about SYK on the quantum computer. So we are entering an era where we can compute few things, even if they can be done quickly using our laptops. Exploring these toy models will hopefully teach us new things about quantum mechanics and computation in general. It is instructive to see that if we can characterize the noise in these quantum devices, we can mitigate and get reasonable results. N greater than 60 is very hard. Probably, I won't say impossible, but very hard for classical computer. And in fact, the eventual goal of understanding four-dimensional superannual theory at finite temperature real time, that is a very distant dream. But these things are interesting to explore on the quantum computers. Hopefully, in the future, it might be possible to study real-time properties of some interacting field theory using these methods. Because these, if they don't work, then probably we don't have any other options of studying this. So that was the talk. I wanted to talk about a few things about the paper. We have the code available on this Zenodo website for if you can run it on an IBM computer. For example, you can make an account here. You get 10 minutes of free runtime on any of the 127 qubit machines. So these are mostly for students or graduate students who are interested. You can write down the circuit, for example, in terms of the gates, which I mentioned. So for example, this is the Hadamard gate, this is the C0 gate. Then you can measure the qubits. So you can play around with these things. And then the answer is in terms of the quasi probability distribution. So I was creating a uniform, I was creating a bell pair basically in this case. So 0, 0 plus 1, 1 over root 2. And this is what you see. This is what you get. You also get some garbage, which you should not get. But as you increase the number of shots, this will rise and they'll eventually come to 1 by 2, 1 by 2. So you can create Bell states, entangled pair, superposition, whatever you can do, time evolution. And yeah, so this is what I wanted to say. Thank you for listening.
Oh, thanks, Raghav, for the wonderful talk. So now we can have some questions. And so, yeah.
So let me ask one question regarding the. I'll also turn on my video. So, so one question that I had was, is it possible, like for instance, you said that the problem with simulating something like BFSS is that the gauge group is too big? Is that a gauge group, or is the gauge group adds complications? Is that the
Yes.
general picture? So is that true even if you're just working with, let's say, a Gaussian matrix model where the gauge group is, let's say, SU2 Gaussian matrix model? Is it a hard thing for a quantum computer?
The only papers I have seen is implementation of one placket SU2 gauge theory in 1+1 or one-dimensional systems. So
see, like, 1+1 is, I think, making it harder, but I'm talking about 0+1.
Yes. So 0+1 BFSS, the entire thing is, can we efficiently write the scalar fields in terms of polymatrices?
Mm-hmm. Yeah. So and
impose the gauge invariance. That is the only, if we can do that efficiently, then we can bring all the tricks of quantum computing and simulate it. Yes. But I think the first step in itself is hard, because representing a Hermitian matrix X n by n matrix in terms of hello.
Sorry, there is some connectivity issue that happened and it got disconnected, and probably some network issues from our side. So I'm using now
see.
my phone to continue with this. So just carry
Oh.
on.
Okay, sure. I don't know. Chetan, are you still there?
I'm not.
Sorry.
It seems like some internet
Yeah.
issues from ISC probably.
Okay, I see.
That might have affected it.
I see. Yeah, because I think I suddenly stopped hearing Chetan. Chetan was saying something and he cut immediately.
Yeah, I think it's probably something happened.
Okay, no problem. We can wait.
Yeah. Let me just wait some more time. And luckily our recording is still on, which is good.
Good. I see.
Yeah, we occasionally have some network issues from time to time. Sometimes suddenly some happens like this. But
I see.
yeah, we keep a alternative network. But yeah, it seems like everybody seems out now.
Yeah, I don't think. Yeah, if the network is.
Yeah, all the people who were using ISC network, they seem to be like disconnected.
Yeah.
Probably some network issues.
Yeah, it's okay. We can wait for like maybe, I don't know, 5 minutes. 5 minutes.
Okay. Just a second. Maybe I check in the other office what happened.
Okay, sure. Yeah.
Yeah.
I'll be here. Don't worry.
Hey, hi, can you hear me?
Yes.
Hi, Raghav. Sorry, my hi. So,
Yeah.
so Mike, I think my question, your answer got cut out precisely at the right time when you're about to say what I wanted to hear. So,
I see.
my question was basically that. So, why were you saying that for n equal to 2, for instance, solving the class, somehow taking care of the gauge invariance is already a hard thing? I mean, I didn't quite understand the point.
No, I'm saying that for SU2 it might still be possible but for higher large n, or it might be hard.
So
SU2 I think.
So what are you trying to do? So what would be what is the goal? So if for SU2, what would you would like to write in terms of gauge invariant configuration?
Yes.
Is that the idea?
Yes. Write down the gauge invariant Hamiltonian in terms of polymatrices. And then try to compute some things basically.
I see. So if you, for instance, if you had like, let's say a matrix model, like a Gaussian matrix model with gauge, U2, a Gaussian matrix model, so first you would want to write everything in terms of the traces and then put it on the lattice. Well, not lattice, sorry, quantum computer. And
that's
that
right.
Would be, the statement is that it's already hard. That's the statement.
I should not say it's already hard, but I have thought about it, but not spent time on it.
Okay.
So I think there might be a way to make it work, at least for the SU2 case. I think it might be possible.
Because I think, I think it would be very interesting if something like a BFSS matrix model can be done, because it's a completely unitary theory, etc. And it's not like SYK, I would say, is slightly less interesting than that if it is doable. If it is not doable, of course, one has to settle for this, because it's a purely unitary theory and we expect it to be a true quantum gravity.
Yes, I completely agree with you on that.
Yeah.
I think if you're interested, we should chat at some later time and see
Sure,
who
yeah,
can.
absolutely. Yeah. I
Yeah,
mean,
yeah.
I don't have anything to contribute in some sense because it sounds like a completely technologically different thing, but I'm happy to chat for sure.
No, yeah. I think it might be nice to put the SU to PF. I don't know how many scale, like we might not be able to do the 9
Yeah,
scalars,
because
but
SU2 is already non-abelian, so it will capture some interesting thing, you know.
yes, I agree.
Yeah.
Yeah, we might be limited by the number of matrices, but we can start with say 3 or whatever. We can
Yeah.
work up from there. Yeah, I think that's.
Yeah,
I'll
anyway,
think
it was a
about
nice
it.
talk.
Right.
It was nice to hear about this because I was kind of curious about this for a while.
I hope it was clear. I tried to make it as simple as I could for
It
the.
was very accessible. Thank you.
Yeah. Thank you so much for inviting. Yeah.
So, Raghav, let's conclude it maybe.
Yeah, sure.
And I will stop the recording and then,
Okay.
I will upload it accordingly with time. So thanks very much
Okay.
for coming and giving a wonderful talk. And
Thank
sorry
you.
it
I
was
hope
very late.
yeah, everyone who was listening. Yeah, thank you so much. Yeah.
Yes. Okay.
Okay, Gaurav. Thank you. Bye-bye.
Yeah. Bye-bye.